Hello everyone, I am Liang, assistant professor at Purdue University. Today I'm very excited to present our work, ModElec. This work was done when I did my PhD at the University of Washington and my internship at HP Labs, in collaboration with my fantastic colleagues, Jarrid, Kris, and Tico. Here's a quick sneak peek of ModElec. It is a design tool that enables designers to integrate the electronic parts with 3D designs before fabrication and assembly. Designers can create 3D circuit layout with 3D printable, highly conductive internal traces with ModElec. The workflow for building a physical computing device looks like this. The maker first creates a physical form by 3D modeling and fabrication techniques such as 3D printing. Then they need to place and assemble the electronic parts in the fabricated 3D form, which involves a lot of manual crafting and wiring. If the electronics don't fit in the form, they need to go back and modify the 3D model. This may result in multiple iterations and a long prototyping cycle. So, our work aims to address a commonly existing problem for prototyping physical computing devices with the 3D printing. The integration of the circuits with 3D printed objects is cumbersome and error-prone. We are not new to tackle this problem. Researchers have explored embedding electronics such as sensors and actuators or computing devices such as mobile phones in 3D printed objects for computation and interaction. Another set of work has explored novel techniques to create conductive circuit traces that can be incorporated into 3D printed objects. The final set of work related to ModElec focuses on the design tools for coordinating electronics and 3D shapes. Well, we have seen various ways to fabricate conductive traces for 3D printing. In the meanwhile, we also have seen the development of conductive 3D printing. Here we want to ask two research questions. How conductive 3D printing can facilitate the design and fabrication process of building devices for physical computing, and what tool support can be provided for such a new workflow. To answer those questions, we developed ModElec, which is a Grasshopper plugin for Rhino 3D modeling. And it allows the designers to control the arrangement of external electronics in the 3D model. Finally, it also generates 3D circuit traces to connect all the embedded parts. The generated traces can be directly 3D printed in place with highly conductive materials. So the entire model, including the plastic body and conductive traces, can be fabricated altogether in one piece. Here on the left side, it shows the design tool interface of ModElec. I'm going to talk more about the panels in a minute. On the right side, it shows the blue 3D model with embedded electronics and generated traces. To inform the user interface, we run semi-structured interviews with several participants. The key takeaway is they need 3D representations of electronic parts with precise dimensions, an easy way to wire parts, and the freedom to explore different circuits. To accomplish all the needs, we proposed a new design workflow with ModElec. All the electronic integration, circuit generation, revisions on 3D models, and also circuit layouts are done during the design phase, and the model can be printed on a conductive 3D printer. Now, here's an example to show all the steps with ModElec. First, ModElec can take in circuit schematics created with three kinds of tools. Currently, ModElec uses open-source 3D representations of electronic parts provided by SparkFun, but the user can also create custom 3D representations using Electronic 3D Package Creator, which is also developed by us. The electronic parts are added to the model as the circuit schematics is loaded. The user selects and moves the parts around by dragging them, and the parts will be automatically snapped to the surface of the model. The user can rotate, protrude, flip the parts in place. Another way is to use a technique called quick positioning to place the part in a position. The user can do fine position tuning by hitting those arrow buttons, which is a technique called part nudging. Before trace generation, we needed to load the printer profile JSON files. which defines the specifications of the 3D printer that we are going to use, so that the tool follows certain rules for trace generation, such as the trace spacings. For trace generation, based on the circuit schematic, the user can preview the logic connections between the parts, which are the red lines here, to inspect whether or not the parts are properly oriented for reasonable routing. With the circuit schematic, the traces are generated automatically, and all the generated traces are listed as well in the interface for selection. The user can revise the model or change the position of the embedded electronic parts. The traces will be updated and regenerated automatically based on the updated 3D model and the circuit layout. Finally, we can add two capacitive touch areas as a switch and manually connect them to the circuit. For manual tracing, the tool allows the user to create the traces between electronic parts, existing traces, and 3D printable regions. For quick positioning, we foxlight the 3D model first and visualize all the possible position candidates on the surface for the user to select. For trace routing, we use a modified A-star path searching algorithm in 3D space. We also created two different socket designs, flat ones for small-scale parts and those with snap-fit guides for a larger part. We also improved how the traces are connected to the part pin pads. For the implementation details, please refer to our paper. To evaluate the usability of the tool, we did a preliminary study with 8 participants. In this study, we provide circuits for 2 tasks, a simple task using a basic LED circuit, and a design challenge to create an electronic-powered gift for Christmas. After the 2 tasks, we did a follow-up questionnaire to measure the usability using systems usability scale and briefly interviewed with the participants. Here shows the 8 Christmas gifts that participants created in the study. On the right side, it also shows how each participant spent their time. Here are some takeaways. Electronic part control is sufficient and helpful, especially the quick positioning feature. There's a learning curve for the logic connection preview and manual tracing. The 3D modeling and electronic integration are still 2 independent flows with ModElec. For the last step, fabrication, we use a multi-jet fusion technology-based 3D printing test bed at HP Labs for model printing. The 3D printing process looks like this. First, the test bed printer dispenses a plastic powder layer. For each layer, the nozzles and selectively fuse non-conductive areas by jetting a special fusing agent. Finally, the layer is finished by fusing an overhead warming lamp on the test bed. Finally, we built 4 applications created with ModElec and printed with the test bed printer. First, we created a spring-based launcher and 2 fracture-based flippers for a pinball game. By connecting them to the external controlling board, we can use them to play the game. The storytelling prop has a turtle ship with a vibrator, a buzzer, and 2 capacitive touch areas. When you touch the head for a long time, you can record your narrative. And tap the head will trigger the story playback. And when you touch the spiky shell, the turtle will buzz and tremble. We can also create non-standard controllers for gaming. For example, here we create a car-like controller for a racing game. To play the game, the player holds the controller and leans towards right or left to control the car direction. The player can control the acceleration and the brake by touching the right and the left touchpads individually. Finally, we created a reconfigurable handheld device that can be used as a flashlight and a fan with different heads attached to the same body. Here it shows how they work in action. There are some limitations to address in the future. First, the route generation may fail in some shapes that do not offer sufficient room for 3D traces. Auto-routing can be optimized by minimizing the overall wiring impedance. Maybe we can use the pick-and-place method to fully use the volumetric 3D model body for electronic integration. And finally, we want to explore more 3D printable sensors. With that, I'd like to end my presentation. The tool is open source, so please check it out. Thank you.